We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system.
Neptune is the farthest planet in our solar system. Thanks to Neil deGrasse Tyson, Pluto was reclassified as a dwarf planet rather than being considered one of the main planets in our solar system. This has brought unprecedented attention to Neptune, which is now the farthest planetary body in our solar system. Neptune's ring system, while not as famous as Saturn's, presents a fascinating and enigmatic spectacle. Spanning approximately 39,700 kilometers in diameter and boasting a relatively narrow width of just 35 kilometers, Neptune's rings reflect the planet's intriguing and complex nature. But there's a lot more to the planet than this. Esteemed scientist and academic Neil deGrasse Tyson has revealed that Neptune is not what we're being told. There's a lot to unpack. Let's get started. The story of Neptune. As the eighth and most distant known planet from the Sun, Neptune stands as a giant in both size and mystery. It is the fourth largest planet in the solar system, standing at 102 sextillion 400 trillion kilograms. For perspective, it is more than 17 times the mass of Earth. Despite being slightly smaller than its neighboring ice giant Uranus, Neptune is denser. The planet lacks a solid surface, being composed primarily of gases and liquids, and it orbits the Sun at a staggering distance of 30.1 astronomical units, which is around 4.5 billion kilometers, completing a single orbit every 164.8 years. Neptune is the dimmest and least visible planet from Earth. We need advanced tools like the Hubble and James Webb Space Telescopes for detailed observation. We're only getting started with all that's weird with the planet. Hang tight, there's a lot more to uncover. For now, let's take a look at things from the very beginning. Neptune's discovery is a remarkable story of human ingenuity. It was the first planet to be located not through direct observation but by mathematical predictions. In the early 19th century, Alexis Bouvard, noticing irregularities in Uranus's orbit, hypothesized that another celestial body was exerting a gravitational pull on the planet. Following Bouvard's death, two mathematicians, John Couch Adams and Urbain Le Verrier, independently calculated Neptune's likely position. On September 23, 1846, Johann Gottfried Galle successfully observed Neptune through a telescope, almost exactly where Le Verrier had predicted, marking a triumph for theoretical astronomy. Neptune's distance from Earth makes it a challenging object of study. Its apparent size is small, and its immense distance from the Sun keeps it dim, requiring large ground-based telescopes with adaptive optics and space telescopes like Hubble for in-depth exploration. Neptune has only been visited once by a spacecraft, Voyager 2, which flew past the planet in August 1989, providing humanity's closest and most detailed glimpse of the distant giant. This brief encounter revealed much about Neptune's atmospheric dynamics, including the presence of a great dark spot similar to Jupiter's famous Great Red Spot. Since then, newer dark spots have been discovered, showcasing Neptune's active and volatile weather, driven by the fastest winds recorded in the solar system, up to 2,100 kilometers per hour. Neptune's atmosphere, like that of the gas giants, is primarily composed of hydrogen and helium, with traces of hydrocarbons and nitrogen. However, it contains a significant amount of ices, such as water, ammonia, and methane, giving Neptune its characteristic blue hue through Rayleigh scattering. Unlike Uranus, Neptune's weather patterns are consistent and intense, its atmosphere brimming with storms and high-speed winds. The planet's extreme distance also leads to one of the coldest outer atmospheres in the solar system, with cloud-top temperatures plunging to negative 218 degrees Celsius, though temperatures at its core soar to an estimated 5,100 degrees Celsius. A faint and fragmented ring system surrounds Neptune, discovered in 1984 and later confirmed by Voyager 2. These rings, known as arcs, remain one of the planet's lesser understood features, but add to its enigmatic charm. Speaking of these rings, there's a lot to unpack here. The mysteries surrounding Neptune's rings. Though not as prominent as those of Saturn, the rings of Neptune form a complex and fascinating structure consisting of 5 principal rings. They were first detected in 1984 during simultaneous observations of a stellar occultation by teams led by Andre Brahick and William B. Hubbard, marking the discovery of arcs within the ring system. These rings were fully revealed during Voyager 2's historic flyby in 1989. So, what do we know so far? While some parts of Neptune's ring system are comparable in density to Saturn's fainter rings, much of it is notably thin and dusty, bearing more resemblance to the rings of Jupiter. The rings are named after significant astronomers who made important contributions to Neptune's discovery and study, including Gale, Leverrier, Lassell, Arago, and Adams. Interestingly, an additional faint ring coincides with the orbit of Neptune's moon Galatea, with 3 more moons, Naiad, Thalassa, and Despina, orbiting within the rings. The discovery of Neptune's rings stretches back to as early as 1846, when William Lassell, who also discovered Neptune's largest moon, Triton, claimed to have observed a ring around the planet. His observation, however, was never confirmed and is thought to have been an artifact of his telescopic equipment. The first confirmed detection came in 1968 during a stellar occultation. Following the discovery of Uranus's rings in 1977, renewed efforts were made to detect rings around Neptune. It wasn't until the 1980s that evidence of a ring system began to solidify. Voyager 2's 1989 flyby finally confirmed the existence of the rings. Since then, the rings of Neptune have been imaged using the Hubble Space Telescope and advanced ground-based telescopes. The brightest rings, Adams and Leverrier, have been observed at methane-absorbed wavelengths, which reduces Neptune's glare and allows for more detailed imaging. However, the fainter rings remain elusive and are difficult to capture with Earth-based telescopes. In 2022, the James Webb Space Telescope made significant progress in observing these fainter rings, providing the first glimpse of them since Voyager 2's flyby. Neptune has a unique ring system that consists of 5 main rings named Gale, Leverrier, Lassell, Arago, and Adams, arranged in increasing distances from the planet. In addition to these clearly defined rings, there may be a faint sheet of material stretching inward from the Leverrier ring and potentially extending even closer to Neptune. 3 of these rings are particularly narrow, with widths of 100 kilometers or less, while the Gale and Lassell rings are much broader, spanning between 2,000 and 5,000 kilometers. The Adams ring is notable for containing 5 distinct bright arcs named Fraternité, Égalité 1 and 2, Liberté, and Courage. These names were inspired by the motto of the French Revolution. 4 of Neptune's inner moons, Naiad, Thalassa, Despina, and Galatea, orbit within the ring system, with Galatea acting as a shepherd moon to the Adams ring, embedded in an unnamed ringlet. Neptune's rings are composed of a high concentration of dust, with the dust fraction ranging between 20% and 70%. This makes it similar to Jupiter's rings, which also have a significant dust fraction in contrast to the more transparent rings of Saturn and Uranus. The particles in the rings are believed to consist of dark material, likely a mixture of ice and radiation-processed organics. They have a reddish color and low reflectivity. The rings themselves are optically thin, meaning they are relatively transparent. Among the individual rings, the Gale ring, named after Johann Gottfried Gale, who first observed Neptune through a telescope, is the innermost ring. The Lassell ring, also known as the Plateau, is the broadest in Neptune's system, spanning from the Leverrier ring to the possible Arago ring at 57,200 kilometers. The possible Arago ring, which may not be a true ring, is a small bright peak located at the outer edge of the Lassell ring. The Adams ring, located at an orbital radius of approximately 63,930 kilometers, is the most thoroughly studied of Neptune's rings and is named after John Couch Adams, one of the co-discoverers of Neptune's position. It is a narrow ring with a width ranging from 15 to 50 kilometers. Neptune's moon, Galatea, orbits just inside the Adams ring and creates a series of radial structures known as wiggles, which have also been used to estimate the moon's mass. The Adams ring is best known for its bright arcs, which were the first elements of Neptune's ring system to be discovered. These arcs are regions where particles cluster mysteriously, rather than dispersing evenly throughout the ring as expected. The 5 short arcs are named Fraternité, Égalité 1 and 2, Liberté, and Courage. Fraternité is the largest, while Courage is the faintest. These arcs are made of microscopic dust particles, evidenced by their enhanced brightness when illuminated by the sun. Though the arcs have been stable since their discovery in the 1980s, there have been notable changes over time, such as the movement of the Courage arc and the dimming of Liberté. Observations by the Hubble Space Telescope and other ground-based telescopes have noted a decrease in overall brightness, particularly in the infrared spectrum. But how the arcs have remained confined is an unresolved mystery. Some suggest that Galatea's gravitational influence helps keep them in place. However, more recent observations have raised doubts about this explanation. Despite various hypotheses, the precise mechanism behind the arc's confinement and longevity continues to puzzle astronomers. Moreover, the arcs show signs of dynamic behavior over time. Observations from Voyager 2, the Hubble Space Telescope, and other telescopes have noted variations in the brightness and size of the arcs. Material seems to move between the arcs, leading to changes in their relative sizes and brightness. Fraternité and Égalité, for instance, have shown irregular shifts in brightness, possibly due to dust being exchanged between them. The overall amount of material in the arcs has remained relatively stable, but certain arcs, like Liberté, have nearly disappeared in recent observations, while Courage has exhibited periodic flaring and dimming. The formation of these arcs remains a mystery. One prominent hypothesis involves tidal forces acting near Neptune's Roche limit, a boundary where the planet's gravitational pull would prevent large bodies from coalescing into a single mass. According to this theory, the arcs might result from interactions between particles in the Adam's ring and Neptune's gravitational field, which causes them to cluster together in certain regions instead of dispersing evenly. But wait, there's more than this to the saga. The moons of Neptune. In addition to the rings, the James Webb Space Telescope captured images of 7 of Neptune's 14 known moons. Among these moons are Despina and Galatea, 2 small but essential shepherd moons. They orbit within the ring system and exert a gravitational influence that helps to confine and shape the rings, preventing the particles from spreading out and dispersing into space. Galatea, in particular, has a pronounced effect on the Adam's ring. It exerts gravitational forces that create subtle resonances within the ring, confining particles within narrow bands. This shepherding mechanism also produces radial wiggles or undulations in the Adam's ring, which have been used to estimate Galatea's mass and further understand its role in ring dynamics. Despina, meanwhile, plays a similar role, working in tandem with Galatea to help maintain the stability of Neptune's delicate ring system. Neptune's largest moon, Triton, is a standout among the planet's satellites due to its unique characteristics and peculiar orbit. In terms of size and mass, Triton is the 7th largest moon in the solar system, with a diameter of approximately 2,700 kilometers, making it slightly smaller than Earth's moon. Triton is by far the most massive of Neptune's moons, accounting for more than 99% of the mass of all of Neptune's satellites combined. Its substantial size and mass contribute to its significant gravitational influence on Neptune and its ring system. One of the most striking features of Triton is its extremely cold surface temperatures, which are among the lowest in the solar system, averaging around -235 degrees Celsius. Triton's surface is composed predominantly of nitrogen ice, with traces of water ice and methane. This icy composition gives the moon its highly reflective mirror-like appearance. Due to its reflectivity, Triton shines brightly in Neptune's skies, particularly in the light of the distant sun. Its icy surface also hosts fascinating geological activity, including nitrogen geysers that periodically erupt from beneath the surface. Driven by the sublimation of nitrogen ice into gas under weak sunlight, these geysers eject plumes of nitrogen gas and dust several kilometers into space. Triton's geological activity, though subtle, suggests the possibility of a subsurface ocean beneath its icy crust. This has intrigued scientists, as it raises the prospect of liquid water, which could be crucial for understanding the Moon's geologic evolution and even the potential for life. Triton's orbit is retrograde, meaning it orbits Neptune in the opposite direction of the planet's rotation. This unusual orbit is rare for large moons and has significant implications for its origin and Neptune's moon system. Triton's retrograde orbit suggests that it did not form around Neptune like the planet's other moons, but was instead captured by Neptune's gravity. One of the leading hypotheses is that Triton originated in the Kuiper Belt, a region of icy bodies beyond Neptune. Triton is thought to have been a dwarf planet similar to Pluto before being captured by Neptune. This capture likely involved a dramatic and violent process, causing Triton to lose energy and settle into its current orbit around Neptune. Triton's arrival would have destabilized the orbits of any pre-existing moons, leading to cosmic collisions or ejections from Neptune's gravitational field. Evidence of this is seen in the chaotic and irregular orbits of Neptune's smaller moons, many of which may have been gravitationally perturbed by Triton's capture. The arrival of Triton could have led to the destruction of some moons, while others were either cast out or forced into new orbits. The retrograde nature of Triton's orbit also means that over time it is slowly spiraling inward toward Neptune due to tidal interactions. Eventually, Triton may either break apart, forming a new ring system around Neptune, or crash into the planet in the distant future. Well, we know where Titan came from. At least we have an idea. But what about Neptune? Planetary migration. The orbits of planets can migrate over time. Giant planets, particularly Neptune, Uranus, Saturn, and Jupiter, did not form in their current positions, but instead migrated to their present orbits after the solar system's formation. This idea emerged from observations and simulations showing that the current structure of the solar system, particularly the outer regions, could not be explained if the planets had remained stationary throughout their history. The migration of the gas giants is believed to have had a profound influence on the arrangement of the planets and smaller bodies, reshaping the architecture of the solar system. The concept of planetary migration is primarily driven by interactions between planets and the surrounding planetesimal disk, which is a collection of smaller, icy bodies that existed in the outer solar system. In the early solar system, when gas giants formed, they were surrounded by a dense protoplanetary disk composed of gas, dust, and planetesimals. These planetesimals exerted gravitational forces on the planets, which in turn affected the planets' orbits. Over time, the cumulative effect of these gravitational interactions caused the gas giants to migrate either inward or outward. One of the most influential models of this migration is the Nice model, named after the city of Nice in France, where it was developed. According to this model, Neptune and Uranus initially formed closer to the Sun, but as they scattered planetesimals, they gradually moved outward. This process also caused the destabilization of smaller bodies in the outer solar system, leading to the creation of the Kuiper Belt and the scattering of objects into the Oort cloud, a distant reservoir of icy bodies. So, why does this happen? Several triggers have been proposed for planetary migration, including gravitational interactions with the gas disk, planetesimal scattering, and resonant interactions between the planets themselves. Early in the solar system's history, the giant planets were embedded in a gas-rich protoplanetary disk. As the planets orbited through this disk, they created waves in the gas, causing them to move inward or outward. This type of migration is known as Type II migration and is thought to have played a major role in the early movement of gas giants like Jupiter and Saturn. Another trigger for migration could be the scattering of planetesimals. As the gas giants interacted gravitationally with these smaller bodies, they flung planetesimals either toward the inner solar system or into distant orbits, in the process altering their own orbits. Resonant interactions between the planets, particularly Jupiter and Saturn, could also have caused shifts in their orbits. The migration of the gas giants had significant effects on the dynamics of the solar system, particularly in the outer regions. One of the most dramatic consequences of planetary migration was the reshaping of the Kuiper Belt. As Neptune migrated outward, it scattered planetesimals in its path, pushing many of them into more distant orbits. Some planetesimals were captured into stable, resonant orbits with Neptune, like Pluto. Many of these objects were also pushed into their present orbits by Neptune's outward migration. Additionally, the migration of Uranus and Neptune may have scattered leftover planetesimals and caused a period of intense bombardment in the inner solar system known as the Late Heavy Bombardment, when many of the solar system's terrestrial planets and moons were pelted with debris. Planetary migration also influenced the orbits of the gas giants themselves, particularly Neptune. As Neptune migrated outward, it interacted gravitationally with the surrounding planetesimal disk, causing it to slowly move away from the Sun. This migration may have played a role in stabilizing Neptune's orbit and could explain why it is located where it is today, rather than closer to or farther from the Sun. The migration also had significant effects on the resonance structure of the Kuiper belt, leading to the trapping of objects in resonant orbits with Neptune and creating gaps in the belt where no stable orbits exist. This process not only shaped the population of Kuiper belt objects, but also influenced the orbital architecture of the entire outer solar system. The migration of the gas giants may also explain the presence of unusual objects like Sedna, which has a highly eccentric orbit that takes it far beyond the Kuiper belt. Sedna's orbit suggests it may have been perturbed by Neptune during its outward migration or by interactions with passing stars or rogue planets in the early solar system. Now onto another intriguing question. What if Neptune collides with Pluto? Although diagrams of the solar system may give the impression that Neptune and Pluto's orbits intersect, and textbooks even mention that Pluto crossed Neptune's orbit in February 1999, the reality is much more complex. A collision between the two celestial bodies is virtually impossible. The reasons for this lie in the unique and intricate orbital dynamics of the two objects. First, the apparent intersection of their orbits is merely an optical illusion. This misconception arises from how we represent the solar system in two dimensions. In reality, Pluto's orbit is significantly tilted relative to Neptune's. This inclination of about 17 degrees ensures that even when Pluto crosses Neptune's orbital plane, the two bodies are never at the same physical point in space. In fact, Pluto remains far above or below Neptune when this crossing occurs. The second and more crucial reason for their avoidance of collision is the phenomenon of orbital resonance. Pluto and Neptune are locked in a 3:2 ratio resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This relationship is stabilized by their gravitational interactions. Essentially, the resonance keeps their orbits in sync in such a way that they are never close enough to pose a collision risk. Even though their paths overlap when viewed from above, Pluto and Neptune are always separated by vast distances, around 2.6 billion kilometers at their closest approach. The orbital resonance also prevents either object from significantly altering its orbit to a point where a collision might become possible. Each planet exerts a gravitational pull on the other, but instead of bringing them together, this interaction regulates their orbits. When Neptune gets closer to Pluto in its orbit, it subtly adjusts Pluto's velocity, ensuring they remain in stable orbits without ever approaching dangerously close. This cosmic ballet has been in place for millions of years, and it will continue to protect both Pluto and Neptune from such a fate. But what if the two do collide? Well, that would be an extraordinary cosmic event with significant consequences. For a collision to occur, the gravitational interactions that keep Pluto and Neptune locked in their resonance would need to break down. This could happen through external influences such as a massive object passing through the solar system or perturbations caused by interactions with other planets or even larger Kuiper belt objects. However, such disruptions are incredibly rare. In the incredibly remote chance that the resonance between Neptune and Pluto was disrupted, a specific sequence of events could lead to a collision. An external gravitational force, perhaps from a passing star, a rogue planet, or a massive Kuiper belt object, could destabilize the resonance. This might push Pluto out of its synchronized orbit with Neptune. Once out of resonance, Pluto's orbit might gradually change, potentially bringing it closer to Neptune's orbital path. Over time, their orbits could begin to overlap in both space and time, something that has never occurred due to the current resonance. As the orbits of Neptune and Pluto intersect, the two bodies might experience closer encounters. Each close pass would increase the gravitational forces acting on both objects, further disrupting their trajectories. A few of these encounters could push Pluto onto a collision course with Neptune. Eventually, without the gravitational safeguards provided by resonance, Pluto could collide with Neptune. Given that Pluto is far smaller, about 0.2% of Neptune's mass, Neptune would not be significantly affected in terms of its orbit or structure, but Pluto would likely be shattered or absorbed by Neptune. Depending on the nature of the impact, some of Pluto's fragments could coalesce into a new moon orbiting Neptune, or the material could form a ring system. Neptune's rings, already faint and composed of dust, might be temporarily enhanced by the impact. In the very distant future, the delicate gravitational dance of the solar system could be disturbed by forces we cannot yet predict. External gravitational influences, such as passing stars or interactions with other planetary systems, could potentially disrupt the orbits of planets, even destabilizing the resonance that protects Pluto and Neptune today. Future exploration and research. Already we know much about the enigmatic giant planet than we did a couple of decades back. The Hubble Space Telescope, with its advanced imaging capabilities, revealed Neptune's 14th moon, a detail that went by unnoticed in 1989 by the Voyager 2 flyby. Designated as S2004N1 in photos taken between 2004 and 2009, it is the latest addition to Neptune's growing family of moons. What makes this discovery remarkable is the size of the moon. S2004N1 is incredibly small, just about 12 miles or 19 kilometers in diameter. Its diminutive size likely explains why Voyager 2 missed it during its flyby. The moon is Neptune's smallest, and its distance from Earth, coupled with its faint visibility, made it especially elusive. The discovery itself was somewhat serendipitous. Mark Showalter, a scientist at the SETI Institute, was studying Neptune's rings in Hubble images when he stumbled upon a faint dot that appeared in multiple images. Through a meticulous process, Showalter was able to identify this object as a moon. To track this tiny celestial body, Showalter developed a procedure that compensated for the rapid movement of moons in space. His computer algorithm predicted where Neptune's moon should appear across sequential images, helping astronomers detect even the smallest, faintest objects. Showalter wasn't specifically searching for a new moon. His focus had been Neptune's rings and peculiar arc formations. But by extending his analysis beyond Neptune's ring system, he repeatedly encountered the same small object, eventually confirming the existence of S2004N1. Despite its size, this little moon has some interesting characteristics. Orbiting Neptune from a distance of about 65,400 miles, it completes a full orbit in just 23 hours. Its rapid orbit and small size make it an intriguing addition to Neptune's complex system of moons and rings. In addition to these exciting discoveries, scientists from the Search for Extraterrestrial Intelligence, or SETI, have long been involved in the search for alien life through the detection of signals from space. While the main focus has been on radio signals, some researchers have noted that in recent years, SETI has detected unexplained signals originating from beyond Neptune. These signals, though not confirmed to be from extraterrestrial sources, have intrigued scientists who are exploring whether they might have come from an advanced alien civilization. Future missions to Neptune are anticipated to include both orbiters and landers, as well as advanced flybys and remote observations. One of the primary goals of these missions will be to conduct a comprehensive study of Neptune's atmosphere, composition, and internal structure. For instance, a proposed mission might involve sending an orbiter to closely examine Neptune's atmospheric composition, magnetic field, and ring system, and to perform detailed imaging of its moons. This could include high-resolution observations of Neptune's weather patterns, which are currently only partially understood. Instruments designed to analyze the planet's atmospheric gases could reveal more about its meteorological dynamics and chemical composition, improving our understanding of its climate and weather. Another goal is to investigate Neptune's icy moons, particularly Triton, which holds the promise of significant scientific discoveries. Future missions might deploy landers or probes to Triton's surface to analyze its icy composition, assess its geological activity, and search for signs of a subsurface ocean. These missions could also include atmospheric probes to study Triton's thin atmosphere and geysers. Understanding Triton's retrograde orbit and its similarities to Kuiper Belt objects could provide valuable insights into its origin and evolution. Understanding Neptune's formation is crucial for broader planetary science. By examining the planet's core, atmospheric composition, and ring system, scientists hope to glean insights into the formation processes of ice giants. This could help refine models of planetary formation and migration, contributing to our knowledge of how planets form and evolve in other star systems. Neptune's unique characteristics, such as its large moon Triton and its unusual ring system, offer a natural laboratory for studying planetary processes that may be applicable to exoplanetary systems as well. The broader implications of these discoveries extend to our understanding of planetary systems both within and beyond our solar system. Neptune-like exoplanets, often referred to as ice giants, have been detected around other stars, and insights gained from studying Neptune could be applied to these distant worlds. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.